Hey everyone, Scott Roberts here with Explore Now, and my special guest tonight is Dr. Katherine Auld. Katherine Auld is an assistant professor at Northwest Arkansas Community College. She is also the astronomy coordinator for the college as well. She is a NASA Solar System ambassador. I've known her for several years now, and she is someone that is super enthusiastic about astronomy, space missions. Her PhD had to do with support for the Mars missions. So, and she's told me that she would definitely be the first to raise her hand if they had volunteers to go to Mars. So, anyways, thanks for joining us today, Katherine.
Thank you for
How
having
did
me.
you? What was your kind of early interest in astronomy and space exploration?
Well, I mean, it dates all the way back to when I was a little kid. I grew up in Central Texas, 100 miles from pretty much anything. And I would go out with my grandmother and watch the Perseid meteor showers with, grape juice and crackers. Um, and so started there. And then I kind of went sideways into geology and came back to space through studying the geology of Mars.
I see. Yeah, and you were teaching geology as well, so
Yes.
right. Uh-huh. And currently, right now, I mean, you're a NASA Solar System ambassador. I've been able to join in with you on a couple of those outreach events that you've done. And years ago, we kind of meet up because you wanted to start up a nonprofit organization to develop a planetarium and science center out here in Northwest Arkansas. And miraculously, or maybe not so miraculously, you volunteered to take on moving a giant 24-inch refractor from Swarthmore College. So tell us a little bit about that.
So I was interested in planetarium, went to a planetarium conference in Albuquerque, New Mexico, and then a couple of months later, because of a listserv that I was on, got an email saying, we have this telescope and we want somebody to take it. And one of the other members of the nonprofit was like, oh, yeah, we'll do that. And I
Mm-hmm.
asked her, have you checked how big this telescope is? And she was like, no, no, no. I mean, it said it was big. How big is it?
It's huge.
It's 36 feet
Mm.
long, 24 inches in diameter,
Yeah,
50,000 pounds.
yeah,
And she was like, oh, but we have it. It's here in Northwest Arkansas, and we will build a planetarium and observatory to feature it.
yeah, yeah.
Be
And I
awesome.
can't wait to look through this thing. It's a beautiful historic brochure refractor. And so if you love those old instruments, especially the refractors, they somehow never really get dated. You know, big mirror
No,
telescopes, there's lots of them that are collecting dust. Unfortunately, this telescope was starting to, but I'm really glad that you've rescued this thing. So it's great. It's great. So tonight's program is about the Parker Solar Probe, and I know that it's named after Eugene Parker, who was a researcher, heliospheric researcher, understood the dynamics of our nearest star more than anyone else, I suppose. And right, and this mission from JPL NASA is, or maybe it's not JPL, is it just purely a NASA mission?
oh, no mission is purely NASA. They partner with everybody all
Right,
over the place.
right,
So it's actually not just NASA or JPL. There's several other partners.
right. Okay, all right. Well, I know that the mission was to carry out a lot of the experiments that would be based on Parker's theories about how the sun works. So, and I'm going to let you get into that. But I'm going to recognize some of the people that are with us right now. We have Bergman Scooter. We got John O'Neill from North Carolina Stargazers, or North Carolina Stargazer. He's also very much into outreach. Dusty Haskins, all these people just really love astronomy. Les Chambers says thanks for hosting. Stephen Hauser says hello from Idaho. We have Anshul Puri from Los Angeles, and Brandon McCullum. Okay, he says yay for Arkansas astronomers. So there you go. But anyways, let's go ahead and let you get started. And thanks for joining us.
Well, I'm going to have fun here, so thank you for having me. So as you said, this mission was proposed by Eugene Parker nearly 50 years ago, but it took quite a while for us to have the technology to actually do the mission, and my screen does not want to forward. There we go. So let's start by talking about the sun. We know a lot about the sun, but one of the things that we don't know as much about is the corona. So if we're looking at the sun, we have the core, that's where most of the heat is created in fusion, and then it moves out through the body of the sun, first as radiation and then convection, and then it finally exits the sun. And at the surface, the sun is only 5,800 Kelvin. So let's talk about Kelvin for a second. Kelvin is just another temperature scale. 0 degrees Celsius is the same as 273 Kelvin. So when we're talking about 5,000 Kelvin, it's just think of it as Celsius. It's pretty much the same scale. But what can we really see from Earth? Other than a few dark spots, these splotches, which we call sunspots, we can't really see much. The sun is so far away that we don't see a whole lot, so we really need to get closer. Our sun is really a very dynamic star. We live in the atmosphere of it because from the sun all the way out, well beyond, Pluto and Neptune, all of that is in the realm that the sun influences. So we're looking at two images of the sun. One is from 92, and the one on the left is from 92. The one on the right is from 99. They don't look even remotely similar because our sun is very dynamic. It goes through this cycle. And so you'll have quiet periods. We're currently in a quiet period. And then periods where it's a lot more active. And so we're looking at a solar cycle here, the graph. And this graph, what it actually is telling us, it's showing us is how many sunspots we see on the surface, because sunspots are one of the only things that we can see here from Earth that tells us about the activity of the sun. The sun is really active and it changes, but most of that we can't determine from here unless we look at sunspots. So we need to get closer. When you get really close, this is actually some video from one of the very early portions in the Parker Solar Probe mission. When you get close, all of a sudden you see lots more detail. And so even though there's no sunspots, we see all of these arcs of plasma. Those are the magnetic field of the sun sticking out and the plasma in the sun moving around. And so how are we going to look at the sun and figure out what's there? So the other thing that we can observe from Earth is that we see the solar wind. When we have events on the surface of the sun like that prominence that just exploded a second ago, if that is pointed toward the Earth, then we end up several days later receiving what we call a solar storm. And that is just billions of highly magnetized, mostly ions and neutrinos that bombard the Earth. And so, being able to tell what's going on at the sun really does have an effect on what's going on Earth. But we have two big mysteries that we don't quite understand. As you move away from the surface of the sun, the photosphere, temperature increases. I said that the surface is 5,800 Kelvin. The corona is closer to 1,000,000 Kelvin. And so why? How does it get hotter as you move farther away from the sun? That's completely counterintuitive, and why does this happen? We don't know. The other one is that solar wind. The farther it gets from the sun, the more it is accelerating. And once again, we don't understand the physics behind how that happens. Usually when something starts out with a speed in space, it continues at the same speed until something interacts with it. Well, but solar wind doesn't. It gets continually accelerated. So those are the two big mysteries that the Parker mission is trying to answer right this moment. This is kind of a dated picture. It's an image from before launch, but it actually launched on August the 18th, 2018, from Kennedy Space Center on a Delta IV Heavy. So it launched, and then let's talk just a little bit about the actual spacecraft.
Yeah.
We have this thermal protection system up front that is 6 inches of carbon nanofiber that is protecting the rest of the instrument from that heat. As it gets closer to the sun, let's call from the Earth to the sun a football field.
Okay.
So the Earth is at 100 yards. One end. Dog got in with me.
Yeah.
The sun is at the other. So Mercury is at about the Earth's 28, the sun's 28-yard line. The Parker Solar Probe will get as close as the 4-yard line. So it moves through this entirety of the corona, 1,000,000 Kelvin. I mean, how do we build something that doesn't melt at 1,000,000 Kelvin? Well, you put in 6 inches of carbon nanofiber to protect it. There's also this white cone thing is a cooling system that helps conduct the heat away and allows it to dissipate into space. Mm-hmm. We have a couple of solar cells to help drive the machine, but they don't have to be very effective because they're so close to the sun. So that's one side. The other side, we can see more of the computers and pieces that are collecting data. So the magnetometer, it is collecting information about Earth's magnetic field. Whisper is collecting information about the solar wind. And so we have all of these different machines on there collecting information. And so let's talk about the things that we have learned. We're currently in, they just started the 5th close approach.
Okay.
Started on
Catherine,
the 9th of this month.
we
But in
have a couple of questions before we
Okay.
get there. Okay. So Chris Holland, is curious about how many close passes. You talked about how near the Parker Solar Probe will get. Okay. So how many close passes will the Parker Solar Probe do during solar maximum, and how important is solar maximum to the Parker Solar Probe with regards to the solar wind and the corona temperature?
So I'm having to think here. We've completed 4 close passes. It will do a total of 29. Um, but part of the answer to that, how many will it complete during solar maximum,
Mm-hmm.
will depend upon how long this minimum lasts.
That's
We're
right.
currently in a minimum, and it's actually lasting a little longer than normal. Um, so, any astronomical day, we should start seeing more sunspots. But if this cycle behaves mostly like normal, probably the last 3 close approaches will be near or during maximum. And then how much does that affect with the solar wind and all of that? To be perfectly honest, we're not sure. I mean, we have pretty good idea that the temperature in the corona doesn't change a whole lot from minimum to maximum.
Mm-hmm.
But this will be the first time that we'll find out for certain. And that's one of those things that I can't wait to find out.
Yeah, well, it's never been done before, right? So,
Right.
okay. And Jane Lubinsky asked, solar wind gets accelerated. So she's wanting to know, is that related to why the galaxies are accelerating from us as well? Is there any connection?
My best guess is no. The galaxies are accelerating away from us due to the effect of dark matter and dark energy, which is energy that we don't understand yet. And so I may turn around and contradict myself and say, since we don't know why the solar wind is accelerating away, there's no reason that they couldn't be related, but I don't know the answer to that.
We don't know the connection. Yeah, right. So lots of mysteries out there.
Oh, yes.
Right. Okay.
So during the 4 close approaches that we have done already, we learned about that the solar wind is doing these switchbacks. So A shows you an electromagnetic field on the sun that simply extends out from the surface, and that's called an open field.
Mm-hmm.
Most of the fields on the sun do this turnaround and go back into the sun. But there are some that extend out. And so what we've discovered during the 3rd and 4th close approaches is that sometimes those will, it's behaving like a normal closed loop, and then it runs into another closed loop, has an exchange, and a piece of it accelerates out. And so you end up with these, they call them switchbacks. And so then the switchback starts to move away from the sun, and matter gets collected into that switch, the first downward loop. And so you'll have clumps of the solar wind, the matter in the solar wind that gets caught there and then moves out. And we're not really sure how yet, but it seems to be that those clumps are part of the information that we need to figure out to understand why the solar wind gets continually accelerated.
Hmm.
And so at this point, I'm saying that this is what we know, and we don't know why we still don't know the why.
Right.
You know, science, you observe, and then you make a proposal on why, and then you test, and well, that one didn't work. Okay, new proposal. So we're in that new proposal stage because we still don't understand why it continually accelerates out.
Okay. And we have some more people joining us right now. We've got, as I mentioned, Jane Lubinsky and Stephen Hauser has joined us. Gary Palmer from the UK is joining us. He does a lot of solar work. But let's ask you some questions here. Stephen Hauser just made a comment, said, looking forward to increased activity. Solar outreach is a lot more fun when I can show sunspots and proms, right? That's
Yes.
true. So all of us that have H alpha telescopes or just plain white light solar filter telescopes, it's always a lot of fun to show that solar activity. Gary Palmer says, hope all is good. So far so good, Gary. Jane has another question. Are the frequency and magnitude of sunspots related to elevated temperatures that the Earth may experience?
The official answer on that is no. We have not found a causal relationship between sunspots and anything having to do with Earth weather. I personally believe that we are not yet looking at the right parameters. My grandfather was a science person. I mean, he was a rancher, but he helped me track down sunspot data from Japan when I was in high school to do a research project on the sun.
This is not your normal rancher, okay?
No, not a normal Texas rancher.
Right.
I mean, he was interested in all kinds of interesting things. But that data included information on new sunspots each day.
Oh, wow.
And we think that we started seeing a trend between new sunspots and Earth weather. But I have not been able to find a new source. That data ended in 1986. And after that, from what I can find, nobody has been recording the new sunspots each day.
Okay.
So that's actually my pet project right now, is to find a source for that particular piece of data, because I think that may be interesting to look at. But sunspots overall, the official answer is no. So that was a long answer for a short question.
Claude Plymate from the Big Bear Solar Observatory has a question. Okay. He wants to know, are the magnetic switchbacks related to the Alphen waves in the corona?
To tell you the truth, I don't know.
Yeah. Okay. Fair enough. Good question, Claude.
And now I have something new to go and look up and research.
That's right. Chris Holland asks, are these switchbacks above where normal prominences reach?
So no, the first interaction occurs at approximately the level that prominences reach, and then that zigzag moves out. And so at the end they are farther out, but they occur at the approximately the level of normal prominences.
Interesting. Okay.
So the most recent orbit, as I said, started on May 5th, and the instruments were activated at 64.5 million kilometers from the surface, and they will be recording for the next 26 days. And we will, find out more. But That's sort of the end of what I had to say, simply because we've been working on this project for a long time, but 4 orbits is just barely enough to scratch the surface. So I have to keep watching. So, any other questions?
Well, yeah, actually. Stephen Hauser just made a comment that we have a very long record of both sunspots and temperatures, which is true. Gary Palmer wanted to know, what are your thoughts on the increase in coronal holes through the solar minimum, and if this contributes to changes in climate here? Around the start of minimum, we have seen more extreme weather. Is it coincidence, or is there any connection?
Officially, the experts keep telling me that it's coincidence, that there's not a connection. I don't believe it. I think that there's a connection. I think we're just not looking at the right variables yet.
Mm-hmm.
So,
Okay.
but yeah, you're right that the coronal holes have been much more active this cycle, and I'm going to go way back.
All right.
We see that the peak on cycle 24 was lower than the cycles before. We do have evidence of 2 different times in recorded history that the solar minimum was so low as to effectively not occur. We have the Maunder minimum, is what it's called, and that interestingly closely corresponds to famines in a couple parts of the world, particularly Ireland. And this is, I don't have enough information to put it together and figure out what the relationship is. I can't see how there couldn't be more connection between the sun and the earth than, what we have believed for millennia. Right. It shines brightly, it stays the same. No, it doesn't. We need to learn more about the sun.
Absolutely. Well, I think we're going to find out a lot more from the Parker Solar Probe. Let me ask you a question. When does the whole mission end?
Well, it's 29 orbits, and so I don't actually remember. I should know that.
Okay. That's okay. Bergman Scooters asks, could the solar wind increase be due to, as it moves away from the gravitational pull of the sun, and the stored energy of the wave accelerates itself? So maybe there's like a whiplash motion or something like that. I remember I went to see the total eclipse from Mauna Kea. So I was part of the NOVA film crew for that. And, we're shooting this on film. The researchers that were there on Mauna Kea were very, very interested in that disconnect between surface temperatures and, the million-degree corona. And they were able to find the zone, okay, where this would happen, but it really did produce a lot more questions than it answered.
And his suggestion of stored energy in the wave as it moves away from the sun's gravity well, that's not an unreasonable suggestion. I think that's just one that we need to continue doing research on.
Gary Palmer makes an interesting observation. He said he linked the movement of Jupiter's jet stream to the start of extreme weather here. So, of course, a lot of us that study the solar system know that the sun drives, all the weather throughout all the solar system.
Much more than we recognize.
It is the is the mother, the source, you know. So um, Les Chambers was talking about the minimum. I assume that you're talking about the Maunder minimum. I don't remember the dates for the Maunder minimum, but it was like the little ice age or something that happened. It got very cold. It's in recorded history, um, and it created its own extreme weather. So
Right. And, as an astronomy professor, what I'm supposed to teach is that the sun does not drive Earth weather at that fine grained.
hmm.
And I have a problem teaching this because
Hmm.
I'm not sure that I believe it.
I'm with you. I'm with you. I think a lot of people who observe the sun would agree with that. Jane Lubinsky asks, why is there an 11-year cycle in the Earth's activity, in the sun's activity, excuse me? What may be the chemical impetus for this?
So, as far as chemical impetus, I do not know. So, what we know is that there's an 11-year cycle, and every 2 cycles on about a 22-year cycle, the north and south pole of the sun flip. Um, and sunspots also do this weird thing where, you know, during the maximum, they start near the equator of the sun, and then they spread toward the poles until you get to the minimum, and then they stop. And
Mm-hmm.
then during the next maximum, they start at the center and spread away from the poles or away from the equator. And so, somehow the electromagnetic field in there, the reason that sunspots happen, the electromagnetic field on the Earth is a nice solid ball. And so the field lines are nice and stable and organized. The sun is a ball of plasma, superheated gas. So as it spins, those field lines spin faster at the equator than they do at the poles, and they get all jumbled up, and the field line sticks out. And the electromagnetic field of the sun is so strong that it pushes the light and energy away. We all, as kids, played with magnets, and you tried to push the 2 magnet ends, the 2 north poles together, and they wouldn't go. Well, on the sun, that field lines are so strong that they will actually push light out of the way.
Mm-hmm.
But it flips on 22-year cycle. And, chemical source for that might be. Um, I don't know.
Oh no. Okay.
I have to say I don't know a whole lot more often than I like.
that's why you're. That's why you study this stuff. Paul Waddell asks: is the Parker data radioed to Earth in real time, or recorded and transmitted when the probe is at a more favorable apparent angle with respect to the sun?
It is stored on the spacecraft. Well, some of it is radioed back real live, but most of it is stored and then sent home when it's at a better angle and not as close.
Nice.
The actually the solar wind and everything will interfere with collection of the radio information.
Yeah, it would be interesting to know. I mean, if you could sit in, at mission control when they're getting, they're in at their close point, I would imagine that they probably give a lot of the instrument a rest just so that it can do the job of collecting data during this time. Might be fairly exciting to watch in real time how it's going, but well, if you overtax the system, it might not be a good thing, So
No, it spends a lot of energy just keeping cool during that point.
yeah, I hope so. Yeah. Um, Stephen Hauser had a history question. He wanted to know when did astronomers first start looking at the sun in different wavelengths, H alpha, calcium K, etc. I think I know the answer to this one. Okay. One of my heroes of all time is George Ellery Hale. Now, I believe that his invention of the spectroheliograph, where he could look at the spectrum of the sun, was really the beginning of that. Is that correct?
Yes, that is correct.
Okay. So that would
Up
have been about
until that
1920 something, right?
20 something, up until that, we didn't have the ability to break the sunlight and record it at the same time.
I see. I see. Um, and then Jane Lubinsky makes another observation. She said, yes, it kind of defies reason about what Earth and Sun relationship with the weather. But there's a lot we don't know. That's the reason why we built a spacecraft to go there, right? So,
Right.
right. Well, gosh, we're kind of at the end of our time. Catherine, is there any lasting words you'd like to give our audience here?
My only lasting words is that I hope the weather's good on Saturday and SpaceX can launch.
Yes, I think we were all watching that. So I do want to thank you very much.
Thank you.
And I want to thank our viewing audience tonight. We certainly have a lot more coming up on Explore Now. One of the programs that we have, it will be with some guys that are really into the sun, which would be Michael Zeiler and Michael Backich from Astronomy Magazine. Michael Zeiler is the guy behind the Great Solar Eclipse, or the Great American Eclipse, excuse me. And they put together this beautiful hardbound book about Atlas of Solar Eclipses from 2020 to 2045. So you're going to watch for that. And earlier we did a program with David Eicher about the galaxies inside the universe's star cities. And that book is actually out now. So I got my copy delivered to me today. And so if you love galaxies, you're going to want to get a copy of this. And certainly if you're an eclipse chaser, you have to have a copy of that. So anyways, thank you very much for watching. We appreciate all that you guys do for us, and we've got a lot more to come. Keep looking up.